So let's look at a circuit now that has both resistors and capacitors, right? If I have a battery in here and I throw a switch and start the current, charge will build up on this capacitor, right? And so if we say that the current is positive charges, right, I get a current that runs through here, and charge builds up on this capacitor. Because a capacitor doesn't allow charge to cross it, eventually enough charge builds up on the capacitor that the current stops. It just charges up the capacitor and there's no more current. And so if you were to draw a graph of the current versus time through the resistor, you would see this. It would start out at some current I naught, we'll say. We'll start it at I naught, and then it'll just taper down to zero as asymptotically, kind of, as the capacitor fills up with charge. Obviously, on the other plate, we're getting negative charges because they're attracted to the other side. And eventually, this guy fills up, and after sort of an infinite amount of time, the capacitor is full. And so the formula for the current through the resistor is the current is I is equal to I naught, and it's e to the minus t, where t is time, over RC, where R is the resistance of the resistor and C is the capacitance of the capacitor. And so you can probably tell, if you remember your algebra, that this is a decaying exponential. That's what this graph is. This is I equals I naught e to the minus t over RC. That's what that graph is. And I naught is just V divided by R, where V is the voltage in your battery and R is the resistance in your circuit. The idea is, if there's no charge on the capacitor and you start the current flowing, so you throw a switch with no current, with no charge on the capacitor, then the current just flows freely initially through the wire, and so Ohm's law determines the initial current. But once the current starts building up, which is instantly, this equation then governs the current flow. And so if we wanted to, we could write I is equal to, I is equal to, instead of I naught, we could write V over R e to the minus t over RC. And notice if, it doesn't really look like a t, that's a little better. And notice if t is equal to 0, it's e to the minus 0 over RC, which is just e to the minus 0, which is just e to the 0, and that's just 1. And so if t is 0, I get my I naught back. I is equal to V over R. Okay, so we'll talk just a little bit more about this on the next slide. So we just said that the current in the circuit is given by this equation. And even by looking at it, we can sort of see it at least makes sense. When t is equal to 0, I is equal to I naught. It's some initial current, right? Here we decided I naught is just the voltage divided by the resistance, because there's no current on the capacitor, so there's no resistance to charge flow onto it initially. And so we just get the initial current. And then you can see e to the minus t over RC as t increases. E to the minus t over RC becomes a smaller number, and so the current declines, and that's what we saw in the last graph. And so now we're going to talk about the charge on the capacitor as the current runs on. The charge on the capacitor increases, and so it turns out there's a relationship between the charge on the capacitor and time, just like there is between the current through the resistor and time. And the relationship is this: the charge on the capacitor is equal to Q final, which I'll write with a Q sub F, times 1 minus the same thing, e to the minus t over RC, right? And so the Q final is equal to the C for the capacitor times the V for the voltage. If you remember our capacitance equation, it was Q equals CV. And so what this is saying is, look, as this capacitor charges up, the final charge it gets onto it is just the capacitance times the voltage, because eventually there's no current running and all of the voltage on the battery is across the capacitor, and that's what the charge is. And this formula here says that as time increases, the charge builds up from nothing initially. If you put t equals 0, this becomes 1 minus 1, which is 0. And so Q initially is 0. And then as time increases, this term here gets smaller and smaller. And so we approach Q final. And so if you do a graph of little q versus time, versus time, let me just back that up a little bit and put the time there, right? It would look like this if you were to graph that chart. I don't know if you've seen an exponential function that looks like that, but that's what it would look like. This is, and this approaches the number that's being approached here, right? Asymptotically would be this Q final, right? It's going to charge up to that. Okay, and so let me just do a numerical example of this to show you something that I might ask you. So now we can do an example where we have an actual circuit here with values. I have a 10 volt battery and a 20 ohm resistor and a 5 microfarad capacitor. And I can say a few things. I can say, well, what's the initial current, right, for the circuit? The initial current, if a switch is thrown and it's just started so that there's no initial charge on the capacitor, then the initial current is just V divided by R, and that's 10 volts divided by 20 ohms, which is 0.5 amps, right? And so then I can say my current, which is I naught times e to the minus t over RC is equal to 0.5 amps times e to the minus t over R times C is the resistance times the capacitance, right? And so 5 times 20 is 100. And it turns out that, so it's 100 times 10 to the minus 6, which is just 10 to the minus 4. Right? And the units for this come out to be seconds. It turns out that farads times ohms gives you seconds. And so it's times 10 to the minus 4 is the current. And so if I want to know what the current at any time, I can just plug into this equation. As it happens, we often just ask, we create a constant called the time constant for the circuit. And it's the Greek letter tau, and tau is equal to the product of R and C, and so it's equal to 10 to the minus 4 seconds. And we say in one time constant at t equals tau, the current then is just is I naught times e to the minus 1 because it's e to the minus RC over RC. And so it turns out that's equal to I naught times 0.368. That's what 1 over E is, or e to the minus 1. And so the current at t equals 10 to the minus 4 seconds, or t equals 1 time constant, is just 0.368 times 0.5 amps, right, which is 0.184 amps. And so I could plug in anything for t, but usually what we want to know is what the value of the current is at some particular time. Or we might ask the question, what's the charge on the capacitor at some particular time? And so we'll do that on the next screen. So we can look at, if we put some real numbers in here, we can look at the currents, which we did on the last screen. And we have, here we have a 20 ohm resistor, a 5 microfarad capacitor, and a 10 volt voltage source. And so when we throw a switch, this current charges this capacitor so that it ends up with a bunch of plus charges on it, right, and minus charges on the other side. And the current flows according to this equation. I equals I naught, e to the minus t. And this time, instead of putting RC here, I put tau, which is defined as RC. It's just equal to RC. And for this circuit, R times C is 20 ohms times 5 microfarads. A microfarad is 10 to the minus 6 farads. And so 20 times 5 is 100. And so times 10 to the minus 6 gives me 10 to the minus 4. Ohms times farads is seconds. And so that's our time constant. And so you can see when t is equal to 1 time constant, in other words 10 to the minus 4 seconds for this circuit, you get e to the minus 1. And as I said last time, after 1 time constant, our current is reduced by 1 over E, which is about 0.368. And so we ended up with a current at t equals tau. At t equals tau, we got the current to be equal to about 0.184 amps. And we could figure it out with twice that one. We could take e to the minus 2, which is about 0.135 at t equals 2 time constants. My current ends up at about 0.068 amps, something like that, if you just plug in for these guys. And so often they'll talk about circuits in terms of the time constants. So we could also talk about how the capacitor charges, and our formula for that was Q on the capacitor is equal to Q final. Is equal to Q final times 1 minus e to the minus t over tau. Again, that tau is the same thing as the RC, right? And so where Q final, again, from earlier, is just equal to the capacitance of the capacitor times the voltage, and that's 5 microfarads times 10 volts, which is equal to 50 microcoulombs. And so the charge on the capacitor is equal to 50 microcoulombs times 1 minus e to the minus t over tau. And when t is equal to 1 time constant, this is just this just gives Q is equal to 50 microcoulombs times 1 minus e to the minus 1, and that gives us 50 microcoulombs times 0.632, and so I'll just write it down here. No, I won't. I'll put it up here. It's sorry, this is a 50 down here, right? And so it's 50 times 0.632, which is 31.6 about microcoulombs. And so that's where it is. That's what the charge is on the capacitor after one time constant. In other words, after one value of t equals RC, right? If I waited for two values of the time constant, it would be about 43 or something like that. I would have to just recalculate this with a 2 instead of a 1 there. And so usually we look at time in an RC circuit in terms of the time constant, not in terms of some particular number of seconds. We say in one time constant, it's 63% charged. You can kind of see that down here. In two time constants, it's about 86% charged. So let's just work a quick example here and answer some basic questions. Here's a circuit. I changed some of the numbers. It's still a 10-volt battery, but now it's a 50 ohm resistor and a 20 microfarad capacitor, right? And so let's answer a few questions. First of all, what's the initial current? We could ask that question, right? And the initial current, the initial current is just V over R, right? And so that's 10 volts over 50 ohms, which is an initial current of 0.2 amps. So this is a question that I might put on a test, right? I could ask, what's the final charge on the capacitor? That's when it's fully charged, and that's just equal to the capacitance times the voltage, and that's just 20 microfarads times 10 volts, which is 200 microcoulombs, or 2 times 10 to the minus 4 coulombs, right? That would be my Q final. And then I could ask a question like, what is the time constant? Right? And that's just that tau, which is RC, which is 50 ohms times 20 microfarads, which is 1,000 microseconds, or 10 to the minus 3 seconds. So these are the kinds of things I'd ask you on a test.